It is 3:47 a.m. in the ICU at Mount Sinai. In bed 7 lies a 72-year-old post-op cardiac patient. The bedside monitor is streaming raw vitals. Deep in that data stream is a hidden biological signal, a subtle 2 mm ST segment shift. It is not steep enough to trip a standard hospital alarm, and the overnight resident, watching dozens of screens 6 hours into her shift, misses it entirely. The math here is unforgiving. Missing that specific signal costs a life in exactly 14 minutes. Conversely, calling a false code burns $1,000 in wasted response and degrades the human trust required for the next alarm. This exposes the core paradox of medical AI. You can build a deep learning model capable of catching that ST shift with 95% accuracy. But if that model simply triggers a silent alert without explaining why, it is practically useless to the clinician. IBM Watson Health serves as a prominent case study for the risks of deploying models that lack a transparent reasoning layer. A $62 million oncology pilot at MD Anderson was abandoned after the system output recommendations that the hospital's own experts found unexplainable. The industry calls this the fluent confidence problem. Large language models and deep classifiers generate authoritative, eloquent text that sounds linguistically coherent. They wrap their outputs in a tone that begs to be trusted, even when the underlying facts are completely ungrounded. This flowchart illustrates exactly where we are in the architecture tree, positioning agent number 23 as the necessary bridge between reasoning and output. Explainability requires a mechanical guarantee. This diagram maps the applied architecture of the explainable agent. We start on the far left with the signal detection phase, running locally at the bedside edge to protect patient privacy. The perception layer utilizes two parallel heads. The first is a vision transformer, pre-trained on millions of scans, built to analyze raw DICOM imagery and output a high-dimensional feature vector. Simultaneously, the second head, a clinical BERT encoder, pulls contextual embeddings directly from the patient's electronic health record, parsing free text like vital signs and medical history. Both streams run continuously. For the system to be clinically viable, this dual perception data fusion must execute end-to-end in under 500 milliseconds. The outputs feed into a learned gating network. It fuses modalities and splits mathematical uncertainty into two categories. Epistemic uncertainty means the model lacks training data. A score above 0.3 escalates. Aleatoric uncertainty indicates noisy biology. A score above 0.5 flags for repeat measurement. Once the uncertainty is categorized, the system applies temperature scaling. This operation mechanically calibrates and locks the final confidence score based on those raw values. Because this number is locked at the mathematical layer, the text generation engine cannot inflate or alter the system's confidence later in the pipeline. Returning to our flow diagram, we move to the system's most critical regulatory feature, trace recording. Every step of reasoning is hashed into a Merkle tree audit log. An identified ST segment shift is timestamped and cryptographically changed in a previous step. This creates a write-once, replayable ledger. This immutable trace satisfies the post-market monitoring requirements of the EU AI Act. Regulators can rewind the exact decision chain even after the model receives further training. Looking at the next node in the sequence, the pipeline enters the explanation build phase, where the actual prose is constructed for the clinician. To generate text, the system uses a 220 million parameter T5 model. This engine is fine-tuned on 50,000 clinician-curated explanation pairs. The decoder operates under a hard constraint. The LLM is physically forced to cite an exact trace index before outputting sentences. Attempting explanations without a valid index causes the decoder to block the text, defaulting to a generic warning to consult a specialist. This mechanical bottleneck guarantees honesty over eloquence. The model is allowed to be incomplete, but it is never allowed to invent evidence. Taking this architecture out of the sandbox reveals a $15 billion commercial reality in 2026. This timeline illustrates how the space got here, tracking Aidoc's expansion as they establish their AIOS platform as the dominant enterprise integration layer. The scale of deployment is massive. These platforms now operate across nearly 2,000 hospitals, analyzing over 60 million individual scans annually. This slide outlines the competitive landscape. While Aidoc focuses heavily on imaging, players like Viz.ai coordinate time-critical stroke responses, earning real economic validation through CMS add-on comments. PathAI and Page are pushing this architecture into digital pathology. Glass Health applies the same transparent reasoning chains to large language models, building differential diagnoses. As platforms integrate into live clinical environments, they face a severe invisible threat: calibration drift. This chart categorizes specific failure modes. Notice the calibration drift row. A hospital might deploy an agent tuned to a 2024 population, only for the demographics to shift by 2026. Left unchecked, the model outputs confident but inaccurate predictions that clinicians follow blindly. The mitigation requires automated monitors. When the system detects divergence, it triggers a scheduled recalibration. Using temperature scaling on the new patient cohorts, we return to the patient in bed 7 at 3:47 a.m. Agent number 23 isolates the ST segment shift. It correlates the anomaly with an oxygen drop documented in the EHR. It calculates the internal math, clears the 0.3 epistemic uncertainty threshold, and constructs the hash sequence. A human-readable alert fires on the resident's screen, highlighting the exact waveform segment alongside the cited trace index. She sees the clinical evidence immediately and intervenes. Consider the alternate scenario, a false positive. In a 12-hour shift, the system will fire multiple alerts. Instead of a naked alarm, the trace reads, "Artifact due to patient movement." The resident reviews the evidence, dismisses the false alarm in 2 seconds, and prevents a $1,000 rapid response protocol. This dashboard presents the actual field impact of this exact architecture. Pilots running the Explainable Agent loop report distinct measured advantages over black box AI. Systems report 30% earlier detection of chronic exacerbations. Clinician response times drop by 40%, and the false alarm rate is reduced to just 3%. Agent 23 analyzes biological data in a way that mechanically earns the physician's trust. Guaranteeing explainability at the architectural level, it lays the necessary foundation for Agent 24, where we scale this intelligence to manage the operations of an entire hospital.